Okay, so let me just switch off my camera for having a better connection, and let me start. So let me start going to where we are left. So as I said yesterday, I gave a kind of introduction of what are the problems and what are the questions that are at least some of the questions which are interesting to understand better from a theoretical point of view in the context of liquids. And let me just go to quickly to the second part of these lectures. So today I want first to give you an overview of how universal is this property. So how universal is actually this behavior and this equation that we discussed yesterday. And after that, I would like to show to you a derivation of this equation using a different idea, which I think it's very much in the direction of what Oleg was suggesting and discussing at the end of my lecture yesterday. And okay, here we are. And then tomorrow, sorry, not tomorrow, Friday, I want to discuss with you a slightly different setup of problems, which are more related to thermodynamics. But as you will see, obviously, they will have a lot to do with what we are discussing these days. And on purpose, I will try to keep the lecture on Friday a little shorter to give us more time to actually discuss and possibly repeat all things that I said before. While today probably is going to be a bit longer, but let's see how it goes. So, all right. So let's start from the question that we left yesterday. So from a theory point of view, or at least from my personal point of view, the three questions that arise immediately after looking at the dynamics of the liquids and after discussing how to understand it in terms of this phenomenological equation that, as we said, it's usually called K-gap equation, but it was actually found much before in a totally different context, and there is known as the Telegraph Equation. So as you can imagine, that equation is very simple, and but still, the derivation that at least I provide was not that formal, was very phenomenological. So here are the three questions that I will address today. So the first question is this really this phenomena or this kind of dynamics more universal? Is just a property of liquids, or what is behind that? The second question that I want to address today is basically the derivation of this equation. As I repeat many times, the derivation that I provided you yesterday was pretty phenomenological. So today I will show you a different route, a different way to derive these in a more formal perspective. And I will also try to give you many examples, or at least several examples, where this kind of dynamics can be found. And at the end, I will try to map them all together. So the examples that I will give come from very different areas of physics. And so I will try to be brief, but to mention all the, the basics behind that, because probably some of them will not be totally familiar with you. And again, if you want more details, I strongly invite you to read the reviews that we have in Physics Report, where you can find many more information about what I would say. So, okay, so the first thing that I want to discuss with you is, can we have a kind of field theory toy model, or let's say a Lagrangian toy model, where this kind of behavior appears? So why this is nice? This is nice because usually when we write a theory, it's not a very good idea to start from the equations itself. It's better to have an action from which these equations are derived. And from this action, we can extrapolate much more information and we can constrain much more the theory. Now, if one try to introduce a dissipative term in a Lagrangian. And we know the dissipative terms must be odd in time derivatives. So remember that the terms that was coming with dissipation in that equation was I omega divided tau. So this means, and this we know from all, let's say, the fluid dynamics story, that dissipation is linked to friction, and friction is proportional to the velocity, not to the accelerations or to the field itself. So if it's proportional to the velocity in terms of fields, it will be always proportional to the time derivative. Now, why this is a big problem, and this is a big problem that goes much beyond what we will discuss. This is a big problem, which is also very well known since a long time ago, that if you try to very naively introduce a dissipative term, like what I wrote here on the top, so this does not work. And the reason why it doesn't work is that because you can immediately realize that these terms is just a total time derivative. So once you write these terms in the Lagrangian, these terms is basically doing absolutely nothing unless you have some very non-trivial boundary dynamics that we don't want to discuss. So this is a problem that, as I said, is a very well-known problem. It goes back, for example, to the question of how to write diffusion or Brownian motion in terms of a Lagrangian. And it's also a very well-known problem that sometimes is rephrased as, can we find an action for hydrodynamics? So if you think about it, all the time we discuss about hydrodynamics, we never, ever start from an Hamiltonian or a Lagrangian. What we start from are conservation equations, are just the equation of motion themselves, which are nothing else than the constraint that comes from the symmetries of the system. And then what we do is we assume some constitutive relation and we follow. But Navier-Stokes equations, for example, are not derived from any action. So why is that the case? This is the case because exactly of this issue here. So nowadays, we know how to overcome these situations. And there is a lot of progress, especially in the last year. But definitely the techniques which are involved to do that are much more advanced and are basically Kalish-Finger techniques. And I will not basically discuss any of that. But one thing that I want to discuss is basically, let's try to be very simple and very naive. And let's say, well, OK, if I have a single field like this scalar phi here, I cannot write anything like that. Now, what about if I have two of them? So if I have two of them, now what I can do, I can write down an anti-symmetrized term, which is dissipative, which looks like this way, right? And now I can ask myself, what is the effect of this field, of this term? Now, if I do that, basically, the Lagrangian, the action that I have in mind, it's something which is quite weird at first sight. So here you can see it's basically the action for two fields coupled together, and they're coupled in this weird way. And actually, what couples them is this dissipative term. And you see that all the terms have two derivatives on the fields, but this last one has one derivative. So when I will go basically in Fourier, that last term will introduce dissipation. And that's exactly why the coefficient in front of that term is proportional or inversely proportional to what I call tau, which will be our relaxation time. Now, if you solve those two equations, so actually the equations that come from that action, you will immediately verify that the behavior of the solution that you get is totally different if the momentum of this phi, once you go to the Fourier decomposition, it's larger or smaller than a value, and not surprisingly, that value is exactly 1/2c tau, which is exactly our k-gap. Now, for momenta, which are larger than this k-gap, you will see that the solutions, actually the real solutions for these fields, are of this sort here. So in 12, what you see is the following. You see that you have an oscillatory solution, whose frequency is given basically by omega r. Now, the two solutions are not only oscillating, but are also damped by this relaxation time. And they are out of phase in general. So in general, there is a phase shift between the two. And the frequency, so this real frequency, is given by the square root of c squared k squared minus 1 over tau squared, which is exactly what comes out from the K-gap equation. So then you can verify that this solution here, whenever k is larger than this value, omega r, it's real. So this means that these solutions are oscillating in time, and this corresponds indeed to propagating waves. So this would be the regime of my solutions, where basically the waves are, yes, damped, so they will die in time at a certain point, but they oscillate as well. And this will correspond exactly to the regime of the K-gap equation, if you like, where the behavior is solid-like. On the contrary, you can ask yourself what happens if you do the opposite. So if you take a momentum, which is much smaller than that. So if you do that, the solution changes drastically. And now the solution that you see here is oscillating only in space, but it's not propagating in time. So you see that these two solutions are not propagating in time. The only thing that they do is basically decay in time. And this decay now here is proportional not only to the tau, but there is also a k proportionality. So the only thing that is changing is basically that the omega part that was in the cosine now becomes imaginary. So then this part is not anymore a periodic function, it becomes an exponential, and that's why you get these terms here. So these things are not anymore periodic in time. So you can see that, for example, in this solution here, so the time is basically this direction, and in this direction, you don't see absolutely any oscillations. So you see that it's just an exponential damping down. So these solutions are not propagating solutions. There's nothing here that propagates in time. And this corresponds to basically the liquid regime, the regimes where k is too small, and therefore the solutions is just decaying. All right, now we can do more, and we can actually define the average field, so between these two things. And for those of you who are familiar with Keldysh-Finger, you can immediately recognize what this really means, and I will comment a little later. So what we can do is we can look at the correlator, so at the two-point function of this scalar, which is plot here in function of time. And what I want to show you is that basically the behavior of this correlation function in time change dramatically if you pass from high momenta to low momenta. So you can see that when the momenta is high, this correlation function exhibits clear time oscillations. All right, so this is the typical behavior of a wave which is propagating, and of course it also damps, so the amplitude is dying in time. But on the contrary, if you go at momenta which are smaller than this k-gap, you don't see absolutely any oscillations at all. So the oscillations are totally gone, and the only thing that you see is basically some relaxation. Okay, this behavior here is basically the behavior, at least at late time here, that you expect from diffusion. So that's exactly what diffusion is. You will find here an exponential decay given by basically the diffusion constant. So let me tell you a few comments about this toy model. So of course, this toy model is not to be taken too serious. It's just basically the simplest field theory that one can imagine. But you see already this simple field theory exhibit a lot of features which are very similar to what we were discussing yesterday. Now, I want to emphasize that it's not a coincidence at all that there are two fields here. And actually, this is a properties of dissipative systems. In dissipative systems, if you want to write down a field theory, you always need two fields. Okay, and these can be understood much better using more advanced techniques, which are like Keldysh-Finger techniques, where basically the two fields are the fields propagating backwards and forwards in time. Now, this kind of field theory that I show you, I don't want to get too much into the details, but for those of you who are curious or who are expert or who are interested in this, I want to mention that there is a very strong relation with non-Hermitian field theory and with PT symmetry. So these are topics which are kind of hot in the last years, and they have a lot to do in general with dissipative field theories. So I want to stress that the question of understanding the dynamics of liquids from a theoretical point of view, or from a field theory point of view, it's basically the same question of understanding how to formally build field theories where dissipation is there. Okay, so we know very well how to basically describe field theories when dissipation is not there, where temperature is not doing anything. But here for liquids, we know that that is definitely not enough. And this is a topic which I find very interesting, and it's something that is really exploding in the last year. So that's something that I wanted to mention. Now, on another direction, I want to show you now something which is actually much simpler and much older than field theory, and it's just basically electromagnetism. Now, we all know that if you consider electromagnetism now not in vacuum but in matter, our Maxwell equations must be modified, and the Maxwell equation now becomes of this form, where E and B are the standard electric and magnetic field, but then we have to supplement these with what we call the displacement current and what we call the H field. And these H and D fields are related to the B and to the E just by basically the constant of the material, the permittivity and the permeability. And this constant, of course, depends on the material, and they are trivially basically the permittivity of vacuum and the permeability of vacuum if you are in vacuum. And then we have to supplement one thing. We have to say that basically the current in general is proportional to the electric field, and this proportionality condition we call conductivity. Okay, so once you put everybody together, all this system of equation together with this definition is a closed system, and you can solve it. So then, well, then you can think about it. Okay, let's solve it. And when you solve it, you have to do some simple algebraic manipulations, and that's what you find. Now, what you find on the top, the first term on the left and the first term on the right are really the standard equation for electromagnetic waves. So this is exactly what gives you the electromagnetic waves, with the speed of light being 1 over square root of mu epsilon. But if you have a system which is in a medium and the conductivity is non-trivial, you will have an additional effect here. And this effect is, notice how it enters. So it enters as a single derivative now in the electric field. So this is a dissipative term. Now, you are expert nowadays already on this equation. So if we solve this equation, we go back exactly to what we were discussing before. So you see here you have two derivatives in space. So you get a k square. Here you get an omega square. Here you get an omega. You plug everybody together and you find, guess what, our equations. So here you see that the velocity now, of course, is not the velocity of shear waves. Now it's the velocity of light. And the relaxation time in this case is basically given by epsilon divided sigma. And you can realize that basically when sigma is 0, so basically when the medium, there's no effect on the medium, then basically this term vanishes. And here you can immediately verify that, well, I mean, if I solve this equation, I will get immediately a k-gap, which is 1 over 2c tau. So in the terms of electromagnetism, this would be sigma divided 2c epsilon. So if the k-gap is so easily derived from electromagnetism, why nobody ever spoke about these things in electromagnetism? And the answer to this question is that actually people spoke all the time about this k-gap in electromagnetism, but in a totally different way. So the way you solve this equation when you do electromagnetism is not by allowing the frequency to be complex, but by allowing the momentum to be complex. And then what you do is you say the real part of the momentum are my oscillations in space, and the imaginary part is basically what determines the scheme depth. So how much the electromagnetic waves is actually entering my material before time. Now, if you solve that equation, what you find out is that at any frequency, the real part and the imaginary part are given by this simple equation over here. And again, remember that we can define a length scale that I call ds, which is just the inverse of this relaxation part. So now what we want to understand is the behavior of these dynamics. And in order to do that, let's define first one thing. So the first thing that I want to define a parameter which determines basically how much this wave is decaying versus how much this wave is propagating. So basically, you can see this ratio is a dimensionless ratio that told me basically how much the skin depth is compared to lambda. So of course, you can imagine that if basically these things is very large, then you have a lot of lambdas inside, so you have many wavelengths in the propagation length. So this d is basically your propagation length. And this is exactly what happened in this regime here when omega tau is large. So when the frequency is large, you can basically expand these things, and you can see that basically this number becomes very large. All right. And in the opposite regime, which is, remember, the hydrodynamic regime, the small regime, you can expand these things at small frequency. And if you do that, you will see that actually this number over here tends to 1. So basically, if this guy tends to 1 and d is comparable to the wavelength of your system, it means that nothing is propagating. It's what sometimes is called evanescent wave. So here we have basically exactly the same physics. We have two regimes, which is small frequency. The wave, the electromagnetic wave, is basically completely damped and is not propagating anywhere. And then there is another regime where the frequency is high, or at least higher than something. And in that regime, basically, the electromagnetic wave is propagating. And because basically d is much larger than this. So this, at least qualitatively, is exactly the same of the solid-like and the liquid-like regimes for shear waves in liquids, just seen in a totally different perspective. So in terms of complex momentum and not complex frequency. Not only that, but in the regime of large frequency, the equation, basically the K1, so the real part in the equation that I showed you before, becomes exactly omega divided c. So we can just go back for a second here. So if I take here the limit of omega t being very large, you see these terms vanishes. I get just the square root 2 here, the square root 2 cancel, and again the K1 is exactly omega divided c. So this is exactly what we expect from a propagating wave, right? The propagating wave is something where the frequency is linear to the momentum. And not only that, but you can verify that on the contrary, see the imaginary part becomes totally constant. So the propagation length is basically constant. And this equation, you can see that the imaginary part of the momentum here, 1 over 2 c tau, is exactly the K gap. So basically, you get exactly the same expression in this limit. Also, literally same expression. So what I want to say here is that there is a very big qualitative, at least, correspondence between electromagnetic waves and the propagation of shear waves in liquids. And this is very interesting because, in a sense, this pushes you to understand the dynamics of shear waves in liquids as coming from a screening mechanism. Because we know that in electromagnetism, all these effects that I just discussed come from screening, from polarization effects. If there's no medium, there's no polarization, there's no screening, this electromagnetic wave will go forever, no problem. Now, a very interesting question here is if we can understand the same thing in a liquid, and most importantly, what is the quantity which is screened? So in the electromagnetism is the electric field. So in the liquid, of course, the first candidate and probably the correct answer is the stress. Probably the stress is screened and it cannot propagate like in a elastic medium. So this is something that I will come back at the end of this lecture. Now I want just to mention here, I will be very brief because there are really many systems where this come from. Here I will just give you some ideas. So don't take this explanation too serious. And if you find that interesting, just go to the review and you will find more. So one thing which is very related to that is the following. So when we think about liquid, and this will be very important in the last lecture, one extremely important character is anharmonicity. So liquids are different from solids because the potential is strongly anharmonic. Now, therefore, the first thing that you can ask yourself is, okay, then what about I take an anharmonic system or a system which is highly anharmonic? Then I should see a K gap somewhere. And indeed, that's what happened. So if you take the most famous system, which is the sine-Gordon model, so let me just show you the equation. So this is the standard equation, and you see that basically this is a very nonlinear model. So you have a propagation of the wave and the potential, which is sine. And so if you consider these, and of course there is a huge literature on this, I'm not expert and not qualified to to go into the details. But what you will find out is that there are two types of solution here that are, at least in the literature, called fast wave and slow waves. And these two solutions depends on a parameter which basically take into account how much nonlinear is the solution. So if you remove the sine from the sine-Gordon model, what you see is that, of course, the excitation are just wave. So it's just this black line. Okay, so now if you increase the nonlinearities, so if you increase basically the strength of this sine term there, what happens is that you open a gap. And you open a gap and you have two types of waves. One, the fast, and one, the slow. And one of the two is exactly showing a Kane gap. So this is very interesting, in my opinion, and it's very suggestive that, again, nonlinearities are extremely important in liquids. They are related to anharmonicity, and all of them are deeply related with the idea of dissipation. Now, moving from a more to a more theoretical point of view, there is something which it's very profound, which was recently found, which is that basically the dynamics of this K gap comes from something very universal, which is called Quasi Hydrodynamics. And this is the reference for those of you who want to know much more of this. So what is Quasi Hydrodynamics? So Quasi Hydrodynamics is the following. Let's start with a theory that has a set of currents, okay? And these currents are conserved. Now, these currents are conserved because of global symmetries, and of course, conserved charges. The simplest example of these is the electric current and the electric charge, but of course, you can imagine many more. Now, imagine, and let's assume that in these systems, all the currents are conserved apart from one. So you have one operator, whatever it is, which is not conserved. So this operator, at least the two-point function of this operator, now will relax in time with a certain relaxation time, tau. And notice that from a theory point of view, this relaxation is due to a symmetry breaking, because now this operator or the corresponding charge is not conserved anymore because the symmetry that was protecting him, it's broken. So in the limit where this symmetry is very softly broken, this relaxation time is very long. And in particular, if you are in a thermal, let's say, ensemble, usually how you quantify that this relaxation and this breaking is small is that the relaxation is very large compared to the inverse of the temperature. So the inverse of the temperature is the characteristics time scale in a thermal system. Now, if you do that, basically the picture that you have is that if you go now in the complex frequency plane, so this is the real part, and this is the imaginary part. Now, basically, the hydrodynamics windows, it's always a finite momentum being close to the origin. So this means that basically the frequencies are small. So this means basically late time. So of course, you will have some behavior here, which is hydrodynamics, and then you will have a lot of modes, which are far from there. And these are what are called UV or microscopic modes. So these are excitations at short time scales that dies very fast, much faster than basically what is considered in the hydrodynamic limit. Now, this quasi-hydrodynamics corresponds to the fact when there is one single mode here that is, yes, non-hydrodynamics, so it's relaxing with a certain relaxation time, but this relaxation time is small because the system, the symmetry is broken, but very softly. So if this guy here, the symmetry was not broken at all, this guy will be on top. So you can see that basically what we can do, we can enlarge the regimes of hydrodynamics, make it a bit larger, and include this mode. Now here we are assuming that the other modes are still very below, so this can be completely neglected, but this one cannot be neglected anymore. So now what we have to do, we have to enlarge the theory of hydrodynamics to this theory here, and we have to see what happens. Now, for historical reason, let me emphasize that this is also known and done in the previous literature as generalized hydrodynamics. Now, if you do that, so from a formal point of view, if we write equations, what you will find out is that basically your system now will be given by a set of equations, which are conservations of all the objects which are conserved, plus the non-conservation of this operator, which is now not conserved. So this is basically what tells me that it's not conserved. And I'm assuming always that this non-conservation is small, so this tau is large enough. Now, what these people prove, and what is actually quite simple to prove, is that if you have something like that, no matters what are these charges or this current or this operator, the equations that you will end up, it's always the equation that we wrote. So it's always that K-gap equation, at least in leading order in this relaxation time. And now here there are infinite many systems where this happens. So the first system that in which this happened, that I will discuss in much more details, and that's what probably Oleg is more interested in, is elasticity with defects. So this is exactly what happened there, and I will go in much more details in the next 10 minutes or so. But there are other systems that I want to mention to you, and other systems are, for example, Magneto Hydrodynamics, or also superfluid with vortices, or even chiral magnetic wave with axial charge dissipation. So let me just pass very fast over one of these examples before we go to our main points. So chiral magnetic waves. What are chiral magnetic waves? So if you think in nature about the U1 charge for fermions, we know that we have U1 left and U1 right that can be combined basically in axial and vector U1. Now, we know that there is an anomaly. So the U1 current, the U1 axial, is actually anomalous. And this implies a coupling between the two things. So if you forget about the relaxation terms, what you will find out is that the hydrodynamics equation for this U1 current, A means axial, V means vector, rho is the charge density, vector and axial, D is the diffusion constant, chi is what is called a susceptibility, it's just a thermodynamic parameter, and kappa here is the anomaly coefficient, and B, of course, is the magnetic field. So what happened here is that if you switch on a magnetic field, the anomaly is non-trivial. Axial and vector fields now couple together. And what you find out here is a wave, which is called chiral magnetic wave, which is highly discussed in the context of heavy ion collision and recently also in the context of vile semimetals. Now, this is all nice, but it's not true. The reason why this is not true or not perfectly correct is that in nature, the axial charge is not conserved. So the vector charge, the electric one, is obviously conserved, but the axial is not. So now you see that if we introduce a relaxation time to the axial charge, what you find out is that the equation that I wrote here, these two equations, are exactly the equations that I was mentioning before. You have two currents, in this case, the vector and the axial. One is nicely conserved, so this will be basically determined by hydrodynamics, will be mainly diffusive, but the other one is not. And the two are coupled together because there is an anomaly. So then the question is, do we see a K-gap in these systems? And the answer is yes. So the answer is yes, you can actually solve this equation. I'm not giving too much detail. These are just algebra things. But what you will find out is that basically you see the solutions, and this is a solution which is reported in many QCD papers, etc., as a square root. And you see that if the momentum is small enough, this square root is totally imaginary. And you see that there is a K-gap, and this K-gap is given basically by this expression here. Now, of course, we were not the first, to understand this, and there are many papers on that. And here you can see, for example, one paper that I took. So you can clearly see the dynamics of the chiral magnetic wave. So the orange would be the chiral magnetic wave if the axial charge would be conserved. And the green, or yellowish, is basically what happened if you include axial charge dissipation. And this is very important for the observation of this wave. And here you can see, for example, many comments about this in this paper. So the problem is that you can understand is that if this guy here now becomes overdamped, it would be much more difficult to observe than if it was like a straight line here. So there is another place where this happens, which is again hydrodynamics. This is still a different contest. This is the contest of relativistic hydrodynamics. So relativistic hydrodynamics is basically the equivalent of Navier-Stokes equation, but for system with relativistic symmetries. And as you can imagine, it's very relevant for fluids where the speeds of the energy are very high. And the most famous example of all of these is the quark-gluon plasma. So it's this plasma that is formed when you collide together heavy ions at very high energy, and you create a kind of a soup of quarks and gluons. But it's not only the only place where you can find applications of this framework. You can think of cosmological objects like neutron stars or plasmas or things like that. And also there, of course, the standard Navier-Stokes equation are not applicable. So one can think about relativistic hydrodynamics. And of course, this is a well-known subject since hundreds of years. But there is a problem. So the problem is that relativistic hydrodynamics is usually written in terms of the conservation of the stress tensor. Now you see I'm switching a bit. This language is a bit more like high energy language. So here you see the indices are actually space-time indices, and these things are all made covariant. So this is your stress tensor. This is the conservation of the stress tensor, which is nothing else than the conservation of energy and momentum. And this is the constitutive relation. So this is the constitutive relation in relativistic form. This is the energy density, this is the pressure, and this is your shear viscosity. Okay, so this is what you would call the shear tensor. Now the problem, and this is a very well-known problem of this setup, is that written in that way, this theory is not causal. So it violates causality. And the reason why it violates causality is that if you solve that equation, you will find a shear diffusive mode, exactly the same shear diffusive mode that I discussed yesterday, with the only difference that the diffusion constant now is not the viscosity divided the mass density, but the mass density, of course, in relativistic theories has no meaning. So it's basically replaced by the sum of the energy density and the pressure. So if you go to the non-relativistic limit, you can show easily that this term drops down and becomes exactly the mass density. Now, why this is a problem? This is a problem because if you compute the group velocity of this system, of this mode, the group velocity grows with the momentum. So at a certain point, if nothing happens, basically this guy at large momentum will become acausal, will become superluminal. It will go faster than the speed of light. And this is obviously a problem. And of course, it was not a problem before because we were doing non-relativistic theory. So there's no causality defined in such a way. But here, causality is very strong, and it sets actually a bound on diffusive processes. So you can see, and here, for example, is a nice paper where this is shown, that if you impose causality of your theory, you will find out that the diffusivity cannot be too large. And if you do things properly, and the way to do that things properties is what is called Israel-Steward mechanism. So if you follow the Israel-Steward theory, what you get out is this equation. And this equation, again, we have seen it like millions of times. And by the way, I forgot here an omega. There should be an omega everywhere. Sorry about that. So here there is an omega, and here there is an omega as well. So if you do this, so if you write this equation and you solve it, you will basically find again our k gap. So this is again the same structure, omega squared plus I omega plus something k squared. So if you impose that the group velocity is subluminal, you will find basically a relations between the velocities and the diffusive constant. And it's very nice to see that this is perfectly satisfied by the k-gap equation. So in a way, in this theory, the k-gap equation is the equation that solves the problem of causality. So in any way, what I want to convince you is that what we are seeing here and where we start yesterday is only the little tip of the iceberg. And this K-gap equation, or this K-gap dynamics, or whatever we want to call it, it's much more universal. And it's actually everywhere in physics. Here I show you some examples. There are many more. And the interesting thing is that now one can think about the following. So what all these systems, all these things that I said, and all these dynamics have in common? And you can see that coming from different places, this idea of the K-gap arrives for very different reasons. So in elasticity and hydrodynamics, this K-gap was coming from Maxwell and Frenkel interpolation. In quasi-hydrodynamics, this is coming from breaking a symmetry. In Keldy-Schwinger formalism and field theory formalism, this comes putting together propagation, but also including dissipation. And in generalized hydrodynamics, which I didn't mention, this enters by adding to your equation modes which are non-hydrodynamics. So this is a big picture, and I think it's quite fascinating, and it would be very nice to put this all together in a common and very universal language. Now, at this point, so this is a good point to have a little break and to see if you have any questions about what I said before, because now I want to do a totally different things. I want actually to derive very formally these equations starting from a solid and adding defects. So is there any questions so far about what I said, or any urgent things before we go to the discussion at the end? No. Okay. So now I want to start from a totally different perspective. So I want to start, I'm not a liquid anymore, but I want to understand what happens if I start from a solid. And I start thinking of this dynamics from a solid perspective. Now, before going there, I have to say some words. So first of all, what I mean by hydrodynamics at this stage is what people usually mean in a broader sense. So hydrodynamics here for me is not the equivalent of fluid dynamics. Hydrodynamics is just the description, the effective description of whatever system you have in mind at short distance, sorry, at late time. So basically time scales which are larger than, let's say, your microscopic scale, and distances which are larger. So basically we are talking about things which goes slow and things which are large. So that's where hydrodynamics applies. And in this sense, you have to be careful, because then hydrodynamics is much more general than what we call fluid dynamics. So hydrodynamics here, it's not Navier-Stokes equation. Okay, so hydrodynamics here is basically the description of long wavelength and slow variations of a system. And this captures all the dynamics of the infrared modes. And you can see, for example, this is a very famous paper of 50 years ago, where you can do an hydrodynamic theory of crystals. So there's absolutely nothing bad. And at least in this notation, I understand that the naming is not maybe very, very, it's a bit like an oxymoron, but that's what you can do. So in this sense, even elasticity theory, it's an hydrodynamic theory, if you like. It's an hydrodynamic theory of solids. Now, the big question that is the starting point here is, are really, amorphous systems or like liquids very different with respect to solids from the point of view of symmetries? And if yes, what is such a symmetry? And here we want to start from something very simple. Let me just review very briefly one thing about the theory of elasticity. So how theory of elasticity is built? So theory of elasticity is built from the displacement field, which is basically just the vector that connects the initial position of the atoms with the final position of the atoms. And the object, which is usually used, is what is called the strain tensor. Okay, the strain tensor we already discussed yesterday is basically the symmetry derivative of the displacement, and it determines the deformation, the mechanical deformations of your systems. Now, this is the standard theory of elasticity for perfect solid, and this is totally fine, and it works very well. But most of the time, and especially in liquids, but not only in liquids, the displacement has two components. So there is one component which is called the affine displacement, and there is another component which is basically non-affine. So this means that if you actually plot the displacement fields, you will see that there are many defects in the systems. So you can see, for example, this is a snapshot took from a paper, and you can see that there are many regions where actually this displacement show things which looks like vortices, where the displacement field is singular. Okay, so this is related to having non-affine displacement, which means that I'm basically deforming my system, and the points, not all the points are going to the position that we're supposed to go. And this is inevitably present in liquids and in gases, but not in order solids. Notice I wrote order, which I mean solid with no defects. Now, let me tell you a bit more, actually much more, about what this affinity or non-affinity means. So here you can see that this affinity means something very important mathematically, which is that the integral over a closed line of the displacement field is 0. Okay, and this mathematically means that the displacement field can be found integrating the strain tensor. So this in mechanics is known also as Saint-Venant compatibility constraint, and is actually the constraint that the double curl on the strain tensor is 0, which can be also rewritten as the fact that the displacement field is single values. So the derivatives commute on this displacement field. Now, recently, we understood that this non-affinity can be written in a much better form. So the better form to write this is to introduce a current, which now has two indices. This is called higher form current. And it's basically this object. For those of you who are familiar with this structure, this is basically the Hodge dual of this scalar field. And you see now that basically the fact that the derivative commutes on this scalar field, which is the displacement, is just the fact that this current is conserved. So the conservation of this current, you see if I apply the derivative here, this is the Levi-Chilita tensor. So this is just the anti-symmetrized two derivatives on these things, which is exactly what I was showing you before. Why this is very important and very useful? Because you see, these symmetries, which is a very weird symmetry, now can be rewritten using this object in terms of a conservation equation. So affinity means here a conservation of a current. So here there is a symmetry. There is a symmetry, which is basically the symmetry related to this object, which makes sure that basically the displacements are affine. And this is extremely nice because there is a strong connection with symmetries and topology in this system. Now, what non-affinity means. So imagine that we have non-affinity, and this non-affinity can arise for many reasons. In liquids, it arises because basically atoms are not in an equilibrium position. And in solid, it can arise because of defects also. So now, if you do that, you find out that the integral of the displacement around the closed curve is not 0. And you actually define a vector, which is known as the Burger vectors. So this vector here is defined, and all of you that work with dislocation, disclinations, and things like that should be very familiar with this object. So this object can also be derived, at least from dislocation, from Volterra constructions. So from looking at the lattice structure, the static lattice structure. Now for us, what is extremely important is that you see now when you do this, you can derive mathematically that that current that I was telling you is not conserved anymore. So this symmetry is broken. And this symmetry is broken, and at least at leading order is broken exactly in this way, where this object is sometimes called phase relaxation rate. But you can see already immediately where I'm going, because this equation is exactly the same kind of equation that I was telling you before. So if what I told you before is correct, you will see a K-gap should come out from this physics here. And notice that these things is very similar to dislocation in order solid, but not exactly. So here, the defects are in the dynamical fields. So are really in the structure of the displacement. It's not in the static lattice structure. So the static lattice structure, or whatever structure you have, can be perfectly fine. But upon deforming these systems, you will create basically dynamical defects, which are the one introducing microscopically these terms here. Now, what you can do is once we understood this, and this is basically the main fundamental point, we can push this further. So the physics part is exactly what I was telling you. So the physics is that basically there is a symmetry, which is usually called local inversion symmetry breaking, which make the point or the atom itself basically not to be in an equilibrium position anymore, because the forces on the single atoms do not basically average to zero. So you have some kind of residual forces, and then that's why the atoms wants to move a little more to go to equilibrium. And this little more is exactly the non-affine part of the displacement. So now, what is the macroscopic picture? The macroscopic picture is that if you are in a solid, in a perfect solid with no defects, basically what you have is that you have a collective shear wave, which is propagating forever. But when you start putting this relaxation time, this omega that comes from the breaking of this symmetry and that comes from this defect, basically this shear wave cannot propagate anymore forever. It will propagate only for a range which is given by its velocity dividing this rate. And in the in the extreme scenario, it will just not propagate at all. So what happens is that when you introduce this term, shear waves acquire a finite propagation length, which is exactly what we're discussing in the first lecture. So more details about this can be found in this preprint that we put recently. And so now here I want to show you, and here I don't want to scare you, these are just some equations, but I want to show you actually practically how this is done. So what is done is that you have to start from the energy momentum conservation, like I said before. But then when you consider the dynamics of the Goldstone, so the dynamics of basically your phonons, these lambdas are your phonons, you have to introduce, you see, a term which is a relaxation term. So this is a relaxation term because the time derivative of this object is actually proportional to the object itself. So this will give an exponential decay. Okay? And now when you have this equation, you can ask yourself, okay, well, let's solve them. And when you solve them, what you find out is the following. So you find that the shear waves, they have this kind of solution here. And you can see by yourself very simply that if you set this capital omega to 0, basically this guy die, this guy die, this guy die. And what you find out is basically only these terms here, which is the propagation of shear waves. And you see the velocity is instead given by g, which is the shear modulus. Now in figures, what you will find out is that for omega, capital omega equals 0, you will find the dashed line. So you will find that you have a nice shear wave, and you have absolutely 0 imaginary part. But when you put this parameter here, you will start opening a gap. And at the same time, in the diffusive part, you will start having diffusion at low momentum, and then the same collisions that we were discussing yesterday. Now, this is not the end of the story, because you can ask yourself the same thing for longitudinal waves. So for longitudinal waves, things become more complicated. Here I wrote the expression, but I don't want to enter in the details. But there is one thing which is very important. So if you are at 0 omega, you are a solid. So if you are a solid, the longitudinal wave is going pretty fast. It's going at a speed which I wrote here like v2. But if you start putting this capital omega, at low momenta, you will become a liquid. So we know that in a liquid, the velocity must become smaller. And that's exactly what you see. What you see here is that increasing capital omega, you will see that below this circle, the velocity is actually smaller, you see? It becomes smaller, and it becomes exactly the velocity that you would expect in a liquid, dp over d epsilon. And then, at a certain point, you will see a crossover from the velocity that it's in a liquid and the velocity which is in the solid. And not surprisingly, this crossover, it's very well known, and it's called positive sound dispersion. And for example, one reference paper is this paper here, where they see exactly this feature in liquid water. So what they call fast sound is exactly these regimes where sound goes faster. And apparently this is a properties which is very universal in liquid. So this theory not only tells you that this K gap, this theory explains the K gap in the shear wave, but it explains at the same time basically the fast sound dispersion in liquids in the longitudinal sector. And if you put them all together, you will find out that basically this macroscopic theory describes for you basically a gap in the transverse wave, and the crossover in the longitudinal wave. And the two, at least qualitatively, are quite related, so are not far from each other. So the lessons is that we can go from solids to liquid by introducing non-affinities or defects in the displacement vector. And from a theoretical point of view, this is related to this topological symmetry breaking that I discussed before, where this higher form must be basically considered. And the nice thing is that this picture is totally consistent with observation. And at least to my knowledge, this is the first formal derivation from symmetries. So here I'm really taking a theory, assuming that a specific symmetry is broken, and deriving from the equation step by step all the dispersion relation. I'm not assuming absolutely anything apart from this, that the symmetry is broken. So I'm not doing any interpolation or saying now my viscosity becomes something different or the G becomes something different. It's much less phenomenological. And still, not only I derive the K-gap, I derive even the crossover between slow sound and fast sound in liquids. So this, I think it's very interesting. And it's also very interesting in relation to what Oleg was saying yesterday, that basically the microscopic theory here, which is not what I did, it's basically strongly related to these defects. And in our picture, these defects has a lot to do with non-affinity. And the way to quantify these defects is actually through the Burger vectors. So basically this parameter here that I put, which I call omega, is basically microscopically is given by what it is, this object here. So in a way, this Burger vector here acts, the value of this Burger vector here acts as an order parameter, and is deeply related to this. So there is actually a relation, I didn't write it here, that can relate directly this vector to these things. So whenever this vector is 0, this object is 0 as well. And you go back to basically perfect solid. So this object here is basically proportional, if you like, to the density of defects. So the more defects you have, and the more they are active, the more this gap will open, and the more the dynamics at low momenta will become diffusive. So you will become basically more and more liquid. And the funny thing, at least from a theoretical perspective, is that this is related to symmetry. So there is really something fundamental behind, which I think is very nice. And let me conclude this part with some remarks. So the first remark is that in this scenario, the K-gap is derived from symmetries. And we didn't completely, let's say, close the relation between these symmetries with the microscopics, but I deeply believe that the relation has a lot to do with defects. And also, I will say something later about something else. So one important thing is that this is not phenomenological. So of course, Frankel and Maxwell theory is very beautiful. All the physics is there, and all the qualitative picture is there. But the derivation of the equation is not really satisfactory. Here, the derivation is much more formal, and beautifully it matches exactly what these people are saying, apart from one point. So you see, importantly here, the relaxation time a priori has absolutely nothing to do with the Maxwell time. So here comes the question, if, when you do really your experiment, this time, so this gap that opens, it's really connected and related. And I'm not saying qualitatively, I'm saying quantitatively with Maxwell time. So does it really coincide with Maxwell time or not? So a priori, in this scenario, I don't see why that should be the case. Of course, the order of magnitude can be the same, and it's probably the same because the quantity involved will be the same. But in general, the numbers do not match. So I don't find so surprising that some people find in their experiments that basically this time is not exactly the Maxwell time. Now, from a point of view of theory, there is one thing which I find beautiful, which is really the only assumptions here is that there is that symmetry, and that symmetry is broken, nothing else. Now, obviously here, one point which must be improved a lot is what is the meaning of this symmetry from a physical point of view, from a microscopical point of view. And I try to convince you that this meaning is related to non-affinity, is related to defects, and is related to basically these Burger vectors that you have around. Now, this is basically what I prepared for today. I want just to say one thing more, which is related because it was mentioned yesterday in the discussion. So these Burger vectors and this non-affinity, it's actually very important for the mechanical properties of solids and amorphous solids. And in particular, it's deeply related with yielding, and not only with yielding, but as Oleg was mentioning yesterday, this dynamics has a lot to do with the formation of shear transformation zones. And what we did, so I didn't mention it, but you can find it in my work. We recently published a PRL paper where we use this theory indeed to explain and to predict yielding in the stress strain curve of amorphous systems and how basically these shear bands create. So you can really basically connect the two, and you can really use this Burger vector and the dynamics of this Burger vector to explain why these shear bands appear and why they appear at 45 degrees and et cetera, et cetera. So here is basically where I will stop, and then of course I'm open to discuss with you and for questions of any type regarding this lecture or the last one. Thank you.
Matteo, thank you very much for exciting lecture again. And let me please to start discussion from my questions. Let me please to reveal some parallels between your example in magnetic hydrodynamics and plasticity. According to my feeling, and I hope that I have experience concerning magnetic hydrodynamics because during 15 years I was working at theoretical department supervised by Professor Mark Schliomis. He is in fact the father of magnetic liquids, yes, and created practically theory together with Rosenzweig. And of course, we had several discussions and also to establish some parallels between magnetic hydrodynamics and plasticity. According to my feeling, the qualitative difference between magnetic hydrodynamics when the ordering and viscosity and phase transition in magnetic liquids is related to the ordering of magnetic particles, arrows, okay? But the size and energy is too small that they are sensitive to Brownian motion, okay? And as a consequence, ordering and influence on hydrodynamic properties is realized in due to the soft relaxation, because stress is not high, okay? Understandable, because it's typical hydrodynamics with order parameter related to small energy orientationally interacted particles. In comparison with that, plasticity is realized due to the nucleation, growth, and collective effects in defects, dislocations, and more coarse defects with much more energy in comparison with the interaction energy between magnetic particles, okay? Okay, and as a consequence, we need for transition from elastic to plastic flow the high stress, because the yield stress to plasticity is very high. Because we need to realize the ordering of a lot of dislocation ensembles. And as a consequence, according to my feeling and our results, the critical phenomena like magnetic particle orientation, but in our case, defects orientation, is realized very, very sharp in the metastability area, because plasticity the plastically pronounced area is the area with highly ordered defects. Okay? Okay. But the energy for this ordering is very high because it's the yield stress of transition to plasticity. It's huge stress. And as a consequence, this transition is very, very sharp. And relaxation time is also sharp. Especially when we are talking about shockwaves loading, but in quasi-static loading, it's the same because we have very sharp transition from elasticity to plasticity. Okay, and it's a very important difference, but I think that most important difference that dislocation in defects is, according to the nature, is the local broken of symmetry. Okay.
Mm-hmm.
It's a very sharp difference with magnetic hydrodynamics and so on. And another very, according to my feeling, important example, when you are straining, for instance, crystal, yes, and you are realizing the path from elasticity to plasticity, you could see on the free surface a lot of signs of shear bands. It's the area of strain localization. And according to our feeling, quite different physics of plasticity related to collective behavioral defects has very interesting image as really holographic image of numerous shear bands on the surface. Because we have collective modes of defects in the bulk of the volume and surface image as holographic image on the surface. And yes, let me see more. And probably I could stop at the beginning. And what about your opinion concerning that?
Yeah, so I have to say that I'm not expert enough in magneto hydrodynamics to say something very smart. What I know is that there is a modern formulation of magneto hydrodynamics which is very, very similar to what I explained. But the way you have to formulate that is a bit different from what is formulated classically. You can see that basically when you do magneto hydrodynamics, there is some kind of topological symmetry which is also kind of broken, and is related to, if you want, the dynamics of vortices and things like that. Now, regarding the scales, I'm not sure if I understand totally your point, but is your point that basically you will need an enormous magnetic field to see the same energy scale basically in the magneto hydro system, or it's different?
Or not exactly, because for magnetic hydrodynamic effects, we don't need extremely high magnetic fields, because the energy of orientation of magnetic particle is not too high, because the ordering is realized due to the van der Waals interaction between the particle.
So
and magnetic field is not high in this case, as you know.
I see. Yeah, I mean, right now I don't think I have anything extremely smart to say, but I would appreciate if you could send me some references about this magneto hydro stuff.
Okay.
I would be happy. Yeah.
Okay, I will select. Okay, okay. And colleagues, questions, please. I think they are adapting to your information. And let me please, Matteo, to give you some another example that it's idea just visited me due to your lecture and discussion. I think we have at the lab experience and unique opportunities and also experimental opportunities to study living cell dynamics using original interferometer, laser microscope. The principle of the following: the laser beam penetrates into the cell and living cell, and due to the interferometry, we could record the fluctuation inside of the cell, evolution of several heterogeneities. For instance, typical one is so-called transcription bubble. It's like defects responsible for DNA ensemble activity inside of the cell. And we have a lot of experimental data for observation of dynamics and collective modes, because we establish a transition from normal cell to cancerous cell due to the organization like critical phenomena of phase transition in ensemble of transcription bubbles defects. But more also very important that this evolution of bubble as collective modes is reflected on the morphology of the cell surface. Okay? Because one of the traditional way to establish difference between the normal and cancerous cell is the morphology of the cell. But morphology is, in fact, it's a hologram. Okay? And now we have probably unique opportunity and unique experimental data to establish evolution of collective modes of defects, because transcription bubble, they're responsible for transcription effects and morphology of the cells. And this transition is realized, according to my feeling, also as gate momentum states. Maybe it's also a very interesting subject related to our original experimental data.
It's interesting. So are you saying that basically the dynamics of these cells change from being diffusive and hydrodynamics to be propagating and ballistic, or?
No, because you see, now it's practically very exciting direction in the cell, in the physics of cell, and it's the following. There is very strong confirmation that normal cell is a ductile cell, which are responsible for transformation due to the defects inside of the cells. Like it means that normal cell with cell responsible for plasticity, but transition to the cancerous cell is related to more and more fragility.
I see.
It's totally related to the subject of transition from plasticity to fragility. Okay, and I will ask our colleagues at the end of our cycle of discussion to present some experimental data concerning that, because it's extremely interesting subject for application of J momentum states physics. Okay, dear colleagues, please, questions. Okay.
Thank you for your lecture. I have a little question about the difference between relaxation and dissipation and diffraction of waves. I meant that only for neutron liquids we have a situation when we have no difference between relaxation and diffraction of waves. And for another situation, we have a difference always for many materials. And the question is, What's the difference between the relaxation and diffraction of phase in liquids and solids?
Yeah, so basically, from a theoretical point of view, dissipation and relaxations are definitely related, but they're not the same thing. So what I mean, at least what I use as in a language in my lecture with dissipations, are basically finite temperature effects. So for example, we know that if you have diffusion in liquid coming from viscosity, this comes from dissipation. But the dissipation is microscopic. So of course, viscosity implies that macroscopically the particles is losing energy, but collectively, the mode is a diffusive mode. So it's not relaxing unless you put some momentum. Now, on the contrary, what I say relaxation, I say basically something which relaxes with an exponential in time, where this exponential does not depend on the momentum. So it's not a diffusive behavior. It's just really the behavior of something which acquires a lifetime. So it just dies. So that's basically the difference. Of course, the two things, also that kind of relaxation can be related to dissipation in general. So we know that, the higher the temperature, the more this kind of relaxation, change and things like that. But strictly speaking, you are totally right. They're not exactly the same thing. And here there is also something which is very important, which is the difference between microscopic and macroscopic. So, when you talk about dissipation or relaxation, you have always to be precise about which kind of motion or collective dynamics you are describing. Because as you well know, the dynamics is totally different from the microscopic dynamics of the single particles, right? So this is the kind of emergent phenomena. So collective waves are emergent phenomena, and the connection between the microscopic part and the macroscopic part, I think, is a very interesting subject. But it's definitely not easy. So as an example, again, you think about Brownian motion or line equation. Microscopically, the particle is dissipated, there is friction, right? The velocity is dying with friction. But then if you consider the collective motion, there is actually nothing that is propagating with the velocity. There is just diffusion, right? So diffusion arises macroscopically from microscopic particle moving and relaxing. So when you talk about relaxation and dissipation, you have to be very careful. And then, of course, we know that things like diffusion constants are related to dissipation by dissipation fluctuation theorems and all these kind of things. But definitely, the connection between the two is a complicated subject. It's not one-to-one. So relaxation is not the same of dissipation, at least naively.
Okay, thank you very much for the answer.
Okay, Matteo, this discussion excited me also because question concerning relaxation for state close to equilibrium and far from equilibrium is quite different due to the following reason. Because far from equilibrium means that we have some collective modes that are responsible for the states which is far from equilibrium. Yes. And according to this, because dissipation links with definition of entropy. It's true?
Yes.
But if the system is far from equilibrium and feels the influence of collective modes, for instance, collective modes of defects that is typical for plasticity as numerous shear bands, in this case, the phase space of the state of the system is fulfilling not with like in Brownian motion, yes, but with stochastic motion. And in this case, we need to redetermine the entropy definition. Okay? Now, for instance, to use the definition of entropy in Arnold's spirit and so on. But if we will redetermine the definition of entropy, we need to redetermine the definition of temperature. Because temperature for the system that is far from equilibrium is not ordinary temperature according to Boltzmann Gibbs statistics.
Yes. So your point is a very good point. And it's actually, so let me go first on the first point you made. So the first point is totally correct, and maybe it's a better answer that I gave you before. So dissipation, formally speaking, is entropy production. So whenever you have entropy production, you have dissipation. And this is connected to reversibility. So the system becomes irreversible because you are dissipating and because you are producing entropy. And this is also related to the fact that time goes always up and not back. This is because of entropy production. Now, regarding your point, you are absolutely correct. So all hydrodynamics and thermodynamics is valid only if you are close to equilibrium. So remember at the beginning, I was stressing that the time fluctuations must be small. The system must be slow. If you move it too far away, then thermodynamics and hydrodynamics is not valid anymore. And not only you have to redefine temperature and entropy, you don't even know if there is a definition of temperature and entropy. Because to define temperature and entropy, you need thermodynamics ensemble. If you don't have thermodynamics, then we can discuss how to define that thing. So basically, all I said, at least in these lectures, applies to the system. Imagine you take a system and you shake it very fast. You go out of equilibrium. Yes. At a certain point, when you go to late time, this system will equilibrate. At that point, what I said, it's applicable. Before that point, there is absolutely no guarantee that all I said can apply. So if you are completely out of equilibrium and you are very fast mixing things or going away, all I said, it's very questionable. And especially, as you said, already the definition itself, it's questionable. I don't even know how to define certain objects, certain thermodynamics objects, because all I said, it's based on being close to equilibrium. Hydrodynamics is, by definition, the description of the system close to equilibrium. Now, of course, we can discuss what it means close. I mean, how close? That's a different question. But definitely, if you go far away, then you will reach a point where this hydrodynamics description that I show you is not valid anymore. And there, things become much more complicated. And even, let's say, the standard physics concept, like you said, temperature, entropy, but even a phase. What is the phase of matter if you are out of equilibrium? What is a phase transition? What is a phase transition if you are out of equilibrium? How can you define it? So the physics becomes much more complicated there if you're out of equilibrium. Yeah.
Okay, let me please also short comments concerning that, because we felt this situation maybe 30, maybe more years ago when we started to create statistics and thermodynamics of solids with defects. Yes. And I would like to attract your attention that in 1937, it was published a paper by one of the founder of Russian Soviet Union theoretical physics, academician Leontovich, Mikhail Alexandrovich. And then it was published a book, Thermodynamics and Statistical Physics. And only after maybe 40 years on the West, it was a rediscovery of results of Leontovich. Result is the following. The first paper was titled Definition of Non-Equilibrium Free Energy. Yes, when Leontovich proposed the following way. We could use quasi-stationary approximation of thermodynamics after Boltzmann Gibbs if we introduce so-called idea of effective field of the system and effective temperature. In this case, we could redetermine the definition entropy and definition of temperature. For instance, definition of temperature, as you know, we could determine the temperature according to two ways. The classical one, using thermometer, okay? And the second one, to use fluctuation dissipation theorem, is the second one. And we try to use this way to establish effective temperature for plastically deformed monocrystals, because the order parameters for plastically deformed monocrystals is related to the number of shear bands. For plasticity, it's the number of shear bands, in fact. It's degrees of freedom. And analyzing the fluctuation related to numerous shear bands, we made the attempt to define the effective temperature for plastically deformed monocrystals. And I understand that it's a very discussable question concerning the extension of classical thermodynamics for out of equilibrium states. But it was shown for some systems, and I hope that crystals in plasticity and so on, the system could be in this area. Probably the definition of Leontovich could be used. And I would like to say you more that 40 years after Leontovich, it was introduced in the West just heuristical assumption concerning this extension of Boltzmann-Gibbs thermodynamics using so-called super thermodynamics. Salis and so on, maybe you know this name. But it was quite empirical, because Leontovich proposed a really statistical way to generalize thermodynamics for out of equilibrium state. And we try to use this way. I think situation is not too bad, Matteo.
I see. Then yeah, also please send me, because my two concern here is that yes, you can have a definition of effective temperature, but how do you know that is unique? First question. And the second question is, for example, you mentioned dissipation fluctuation theorem, but there is absolutely no proof of that theorem out of equilibrium. To prove that theorem, you need equilibrium. So it's not obvious to me if I have to trust that out of equilibrium. That's also my other concern.
Matteo, I would like to say that by the way, in your papers you have references concerning papers by Kugliandolo. Okay. Kugliandolo, after 40 years after Leontovich, they have used quite similar way for definition of effective temperature for out of equilibrium systems. And concerning your remarks that effective temperature is unique or not, if we could determine degrees of freedom of the systems, which corresponds the specific state, and have experiments concerning these degrees of freedom, we could use a definition of effective temperature. If you want to follow thermodynamics, but we need to follow thermodynamics, because if we don't have thermodynamics, how to develop continuum theory and phenomenology?
Yeah, that's what I was thinking. It's even a question of what you are going to start writing. I don't even know what to start writing. What quantity you are considering? It's not obvious. Yeah, I totally agree.
Okay. It means that, Matteo, we have a lot of exciting questions to discuss. Okay, together.
Yeah, that was very good. Yeah.
And colleagues, please question more. Okay. Matteo, thank you very much. And we are excited by your lecture and also the perspective of joint research. And we are waiting with great interest your next lecture.
Great. So thanks a lot for listening, and I see you all on Friday.
Okay. Thank you very much, Matteo.
Take care.
All the best. To be care.
Bye. See you.
Bye-bye.
See you.